Let's consider metal fatigue at this point. The first type of fatigue loading to consider is repeated or reversed or pure oscillation. The idea here is that the load or the stress in the material varies with respect to time, and in this case what we've got is a load where the stress goes up to a level equivalent to the level it goes down to in the compression region repeatedly over and over again. So the maximum stress on the positive side, the tensile side, is the same magnitude as the stress in the compressive region, which is a negative normal stress. Now, understand we're talking about normal stress at this point in time. The average stress of this cyclic nature is zero. There's no average. I mean, if you average it out over time, you just get zero. But there is an amplitude that is not zero. In order to quantify the oscillations and how they occur and the different types there can be, we need to define a ratio, a stress ratio, that will always be the minimum stress, the most, to the left on the number line, over the maximum stress, which would be as far right on the number line as it could be. In this case, of course, you see that the minimum stress is negative. Since it's equal in absolute value to the maximum stress, then our stress ratio R is just equal to -1. Now this is pure oscillation. This is a basic, in fact, it turns out this is the most damaging type. But what's interesting about fatigue type stresses, or stresses that vary over time, is that they can cause failure in the material at strains or stresses much below the yield or the ultimate strength of the material. So if you just take a dog bone sample and you pull it apart and you find the yield point and the ultimate strength, you might think, well, no problem, I'll use that, and as long as the stress amplitude does not go above, say, the yield strength, everything should be okay. Well, it turns out it's not. It turns out that varying stress is very damaging to the material. And so the endurance strength, or the endurance, if you can call it strain, is much below the levels you would expect just given a simple material test. There's a machine or a test set up, an R.R. Moore fatigue test device. We'll look at it in a second, but it uses a very special specimen. It uses a very polished surface in the region that's going to fail. There's also a very gradual taper in the material. You want to make sure that the material fails at a predictable point, and so you do taper it down, but it's a very gradual taper so that you end up with no stress concentration essentially. The stress ratio, as I mentioned, for this test is -1 because it's a fully reversed bending stress. And basically all you do is you turn on the machine and it rotates the shaft, and you just measure the amount of cycles, the amount of turns until failure. Because let me show you the machine. Here it is. Here's the test fixture. Essentially, you've got a couple of blocks at the end that support the shaft. That's the test specimen. The shaft goes through all 4 of the bearings, and you have a center yoke there where you can apply a load to that yoke. And the center section, if you look at it, is neck down. You can see it there. And that section in between those 2 bearings inside of the yoke, that's the section that's highly polished, and you can see the very generous taper there to avoid stress concentrations. And then all you really do is you just make that shaft rotate. I don't know how you would in that lower figure, or even in the upper figure for that matter. Usually you'd actually have a motor on one side driving it, but the point is you turn this shaft with that load applied and measure the number of turns you get out of it until the shaft breaks, and it'll break in the center there. Now if we consider what's going on with this device and how it's loaded, what kind of stress is being applied, you'll notice it's a fairly clever design. The idea here is that we only want one type of stress. We only want bending stress. And so if you look at a free body diagram of this device with the load W applied to the yoke, then you'll have W over 2 at each of the 4 bearings as the reaction loads. And then if you consider the shear force throughout the shaft, you'll notice that the shear force goes to 0 in between the yoke. And so, the moment is the integral of that shear, and so if we add up the shear over the length essentially, we get a moment of W over 2 times A, where A is the length between the first two bearings on the left. Now that center section then has only the moment WA over 2. It has no shear in it. So what we're doing here is applying a pure bending moment. And notice what happens. As the shaft turns over, the section that was at the top, that would have been in compression, is now on the bottom and it's in tension. And so basically, if you were to ride around on one point of that shaft, you're riding around as the shaft turns, you would measure, if you were a strain gauge or something, you would measure stretching and then compressing, stretching and then compressing over and over, exactly as the diagram that you see. And of course, the maximum stresses, the maximum and minimum stresses would occur at the top and the bottom. And so they would be equal, and if you measured them, then you could measure the number of cycles till failure at that stress. So if you perform this experiment over and over and you put different loads on the yoke and then calculated the stress from that, you could actually plot the number of cycles versus the stress that you're applying to that section in the middle. And what you'd find is that it's not really a surprise, right? I mean, the lower the stress, the more cycles you would expect to get out of that. That makes sense. But what's really interesting is that for steels, you eventually reach a point where the line no longer goes down. It essentially is constant. And what that really means is that as long as the stress that you apply to the material is below that limit, you could put as many cycles on it as you want and it would last forever. And you might think, well, why design something that lasts forever? Nothing lasts forever. Well, some components have to be designed to last forever, or they simply won't last the required life of a regular device. Think about your car, for example. There's a crankshaft in your car, and that crankshaft turns over at the engine RPM. A typical engine RPM anywhere from 1,000 at idle or so to about 3, 4, 5,000, depending on what kind of car you've got. Well, let's just say, for the sake of argument, you're going down the road, you're headed on vacation, and you're going to drive for 8 hours or so, maybe 10 hours. Let's make the math easy, 10 hours. And your crankshaft is turning an average of about, well, again, I'm going to try to make my life easy. This may not be too easy. We'll try it. 3,000 RPM, let's say. Okay. So shaft is turning 3. So every minute you've got 3,000 more cycles on that crankshaft. Well, I'll let you do the math. How many cycles would you have? You might be surprised. It's a whole lot. A lot of engine components in your car have to be designed to last forever, if they're going to last at all. Because really the number of cycles required before you get to this infinite life section over to the right, where the curve tapers off and it's just a straight line, a horizontal line, that many cycles is not all that large. You see it listed here as 1 million. The data is nowhere near this clean. These are average lines from a bunch of experiments. But typically what you try to do is make some sense of them, and these, this horizontal, or these linear lines for the sloping region and the straight region are not bad approximations. They're pretty good, decent, representations of the actual data. And they make our lives easy to work with, so we use them as they are. Now you might notice that there's several steels here. There's some 4140, 4340, and 1020 steels. All of them eventually exhibit this infinite life phenomenon, but aluminum does not. There's 2 aluminums on here, 2024 and 6061. Aluminum does last longer. As you go out, it's less sensitive to stress. You can get more and more cycles out of it, but there's no such thing as infinite fatigue life in aluminum. And that's a little bit scary when you're in an airplane and you look out the window, you happen to get a seat by the wing, and you see that wing out there kind of flapping in the wind, because think about it, the whole weight of the plane, you and everything in that plane, is sitting on those wings. Those wings are literally holding you up in the air. They're just beams that have a tremendous moment at their root and are holding you up in the air. But I'm not trying to make you scared of flying. This is something that's very important. Fatigue is something that has to be understood and used in order to predict failure, so that things don't fail, like airplanes falling out of the sky. You don't want that. We'll talk more about this diagram in a little bit. Now, this fully reversed stress is not the only kind. There are types of fatigue where the stress is not fully reversed. And here's our first example. Now, when the stress is not fully reversed, we will call it a fluctuating stress. So anytime we have a stress that is not fully reversed, therefore the mean stress is not zero, we will call that a fluctuating stress instead of a fully reversed stress. And we're still talking about bending stresses or normal stresses only. We're not talking about shear at this point. As a matter of fact, I'm not going to address shear stresses in this lecture. The chapter reference that I gave you has some discussion on it. You essentially use Moore's circle to combine the shear and normal stress, and then you use the procedures that I'm going to show you in this lecture. But I'll let you look at that on your own. Here's our first example of a non-fully reversed stress. You'll notice here that the minimum stress is 0, and the maximum stress is some value. We don't know what it is. This doesn't matter, some positive tensile value. And so we can still define the amplitude as the half height. The stress ratio is still the minimum stress over the maximum stress. Since the minimum stress is 0, well, then that ratio is 0. And what's interesting about this is that this is a pulsating stress. This does have a special name. Some of the others don't, but this one does. It's a pure pulsating stress. You'll notice that the mean or average stress is not 0, right? It's some positive value. It's half of the maximum stress in this case. So this is our first example. Now, more generally, we can consider a tensile mean stress where the entire fluctuation is above. It's all in the tensile range. And so whether it's the maximum stress or the minimum stress, it's always in tension. So imagine taking a rubber band and stretching it out and then stretching it farther and releasing, but not all the way back. Just you continually cycle the rubber band under tension. That's what's going on here, but with steel or aluminum or whatever the material may be. We can still talk about an average or mean stress. We can still talk about a stress amplitude, a maximum and a minimum. And if you think about the limits of this shape could be moved up or down, and its amplitude could be changed. But as long as that minimum stress is above the axis, then the stress ratio will vary from 0 to somewhere between 0 and 1. Because if you think about it, the only way you could get a 0 is if this fluctuation moves all the way down to where it's touching the 0 line. On the other hand, the other limit to get 1, you'd have to take the maximum and minimum stresses so high that they're approaching 1, so or where their ratio is approaching 1. But since the minimum stress is always less than the max, it would always be strictly less than 1 in the stress ratio. But the point here, and the really important thing to get, is that all the stresses are tensile. You see, fatigue is very sensitive to tensile stress, not so much to compressive stress. And so this is a pretty bad situation because all the stresses are tensile. Now, it turns out it's not quite as bad as the situation where you have fully reversed stress. Fortunately for us, or unfortunately, however you want to look at it, that type of stress where it's fully reversed is pretty much the worst type of stress that you can encounter. Now, another type, if we take that whole curve and we move it down a little bit, where the minimum stress is now in the compressive region, well, notice our maximum stress is tensile still, the compressive, or the minimum stress is compressive. The average, as long as we don't move down too far so that we get to a 0 mean stress, the mean stress will be a tensile stress. Okay, so this is a tensile mean stress example. And then the ratio is going to be between -1. Now that's the case where the mean stress is almost down to the 0 stress line, and so the minimum stress is almost equal to the maximum stress, at least in magnitude, so you get -1 as the ratio, or 0. And now the 0 is the other limit where this fluctuation curve has moved up so that the minimum stress is 0. And so the ratio of the minimum to the maximum stress varies between -1 and 0 for this tensile mean stress, where the maximum stress is tensile, the minimum stress is compressive. Now if we keep moving that curve down, remember we're going to skip over the fully reversed version because we've already addressed that. If we keep moving this curve down so that the maximum stress is still tensile and the minimum stress is compressive, but now the mean stress is below 0, then we have a compressive mean stress. In this case, if you think about the limits, basically you're always going to get negative, first of all, because you've got a negative or a compressive minimum stress. So that's going to be in the numerator. The maximum stress is above the 0 line. It's positive. It's tensile. So you'll always get a negative over positive. It's always going to be negative. ratio. But the limits here are between negative infinity and negative 1. And the reason it's negative infinity, if you think about the limit, if that curve moves down so that sigma max goes to the 0 line or very near it, well then sigma min, which is a negative thing, divided by 0 roughly, is going to approach negative infinity. So that's that left-hand limit. The right-hand limit, what's going on there, the limit is just a zero mean stress, which we've already addressed. So this is a compressive mean stress where the tensile, the maximum stress is tensile and the minimum stress is compressive. But the average is a compressive stress. Now if we keep moving that curve down farther, we'll still have a compressive mean stress, but now all of the stresses, the maximum and minimum, are compressive. And so they're going to both be negative, so negative over negative, we're always going to get a stress ratio that is positive. And of course, as we move it down farther and farther and farther, sigma max and sigma min approach each other. That ratio then approaches 1. And as we move this closer and closer to where sigma max is approaching 0, again, it's in the denominator, so that would approach positive infinity. It's going to be negative, but close to 0. So the minimum stress that's negative divided by a very small negative maximum stress will get you close to infinity. So there are the stress ratios for various types of fatigue loading or fluctuating stresses. Here's an example, and I do want you to go through the example problems in the text. Make sure you go through it and find all the example problems, at least in the sections that I've referenced in these slides. You'll recognize them as you go through. But look through his example problems, because they're very good, and they'll teach you a lot about fatigue failure. I've got my own examples I want to work for you, and you'll view those as well later. Now, look at this device. There's a cam on the left-hand side that rotates, and it pushes a follower. And it can only push the follower to the right because there's just slippage between the cam and the follower. There's a spring. It's just a horizontal, or not horizontal, but a vertical beam that acts as a spring to push the follower back every time the cam rotates to a minimum position. And so this is just a cantilevered beam where the cam, if it just rotates continuously, is pushing the follower to bend the spring over and over. And if you think about the stress at the root of that cantilevered beam, well, there's a stress that's applied and then relieved. Now, maybe the spring is always under some stress. Maybe it's always bent to the side a little bit. In that case, the stress is never fully relieved. But this is the setup for the example problem. And I think, if I remember right, he did set it up so the stress is never relieved. And so the maximum and the minimum stresses, well, it depends on which side you look at, right? Because on the right-hand side of this beam, they are what? Compressive stresses. On the left-hand side, they're tensile stresses. So if you were to expect fatigue failure, you should expect it on the left-hand side because that's where there's tension. And if that tension is constant, it just increases and then comes back to some value above 0 that's still a tensile stress. So go through that example. I think it will help you understand fatigue a bit better. There are some types of stresses or loads that are outside the scope of this course, and those are shock or impact loadings or random loads. For shock and impact, there are other methods that are used for analyzing to make sure there's no failure. Examples of this are pile drivers, where a weight is essentially dropped on top of a column to drive that column into the ground, which is basically the same thing you're doing with a hammer and nail. It's just a really big hammer and a really big nail, and you're nailing into ground instead of typically wood. But a hammer and nail is the same type of load, and these are loads that we will not analyze in this course. We're not looking at loads that are applied very, very suddenly. We're looking at loads that are applied gradually over time. Now, they may be applied very fast. They may be applied multiple times per second, but there's not this sudden onset of load like an impact or the resulting shock. Other types of machines that do use this type of loading to advantage are rock crushers. What's shown here is I think it's Barmac. I always get it confused, either Balmac or Barmac. I'm pretty sure it's Barmac. Rock crusher, and what this thing does, it has a vertical axis that spins, and if you drop rocks into it, and these are huge things, okay? You're not going to drop a handful of rocks in. You could drop car-sized things sometimes into some of these. They can be very large. But what it does is it slings the rocks out. Eventually rocks collect around the periphery of it, and basically you have rocks smashing into rocks, and it's a pretty clever thing because the machine can last a long time, or relatively long time, smashing rocks because it's using the rocks to smash themselves. But anyway, we won't cover any of these types. And if there's a random type of loading where it just varies, at random, we're not going to consider that either. You have to somehow characterize that random signal using statistical methods and then go through what we're learning in this course. Alright, so basically fatigue occurs due to crack propagation. Now they used to think that it was crystallization of the metal because of the way that the failures looked. You'd have a shaft or something's broke apart, you could look at the ends and it looked like that there were crystals forming or something. So it's called crystallization, but that wasn't really what was going on. The metal was not crystallizing. Well, what happened instead is there's very small, minute cracks, and those cracks propagate, and fatigue is the name we give that, really. The cracks can occur from many different sources. There can be, if you make a part, the surface is not going to be perfect. There might be cracks just in the surface. There could be even roughness in the surface can provide a small enough crack where there's enough stress concentration that the crack can open every time it's pulled apart. Basically what happens, think about a piece of paper, for example, where the piece of paper has a very small rip in it. If you start applying tension to this over and over and over, you eventually break it. Right? You eventually get to a point where it just can't take the load anymore. And so that's essentially what happens with metals. Now, so surface roughness can be a point where cracks can begin and propagate from. There can be imperfections in the bulk of the material. If there's some inner point of the material where there's a missing material, and there's just imagine a bar of metal that's being pulled apart repeatedly, eventually that crack on the inside is going to grow. The surface finish can cause metal to fatigue. If you've got a very rough surface finish because of the way that the item is processed or made, that can be a place where fatigue cracks can grow, or begin at least. Even grain boundaries can potentially be sites for beginning crack propagation. Now, the areas of the material that are particularly vulnerable to fatigue are areas where there's very high stresses and also where there are concentrations of stresses, because that stress concentrations generate high stresses in a very localized area. So those are the areas that are vulnerable, essentially just high stress areas. And the issue with fatigue is that it can cause sudden and very catastrophic failure where you don't expect anything. You don't see any necking down like you do when you take a dog bone and you pull it apart slowly in a tensile machine. Rather, what happens is you don't notice that there's a crack growing, and all of a sudden the part fails, and it can be a catastrophe. As a matter of fact, it has been in the past. I'm trying to learn how to say the man's name. I don't know if it's Trevithick's or how you say it, but anyway, he was one of the first people to make a commercial locomotive. You can call it commercial. He worked for an ironworks, as I understand the story goes, and the person who owned the ironworks wanted a machine that could take iron down to a canal. It was, I guess, some distance away. And so this man, Richard Trevithick, I think you say, or Richard Trevithick, he built a locomotive called the penny derring, and you can see it here. It's fairly unwieldy. If I remember the story right, the first run out, he carried, I believe, 70 people in a car and 10 tons of iron down to the canal. Interestingly enough, this locomotive, one of the very first ones, only made 3 trips in total in its initial service. And after that, it was retired. The reason is because every time it made a trip out, it broke the rails. And so the rails had to be repaired, and the owner of the company, the ironworks, decided that maybe we should just use horses, I guess. I don't know, whatever they used. But certainly didn't think this newfangled steam engine thing was going to be very good, I guess. Obviously that, problems were worked out, and eventually steam engines became a thing. But this is one of the first steam engines, and the first I know of that is a commercial steam engine. But what would happen with these things is a sudden catastrophic failure. As a matter of fact, there was a reproduction of this steam engine made, and it was a show. I don't remember the date. It was, I think, 1990s at some point. I wasn't there. I read about it, and the engine was pulling something, and one of the wheels came off. The axle failed that connect the two wheels, and sure enough, it was a fatigue failure. The same kind of problems that plagued this machine. So I guess, if you don't update designs, if you build the same thing, you can expect the same results. And at least it was consistent, I suppose. But anyway, this has led to not just sudden failure where the engine was retired and never used again. This has led to loss of life. The Versailles rail accident of May 8th, 1842 was a big issue. I've read that anywhere from 55 to 100 people, I don't know the actual count, I'm not sure that anyone does, that's how many people lost their life in this accident. There was this train pulling carloads of people, and at that time apparently people were locked into the cars. It was very tragic. There were two engines pulling all these cars, from what I understand. They were going from Versailles to Paris, and they were on the outskirts of Paris. They were almost done with their trip, from what I understand, and one of the front axles, the front wheels, fell off of the front locomotive. The locomotive behind it plowed into the front of the locomotive, immediately killing the engineer and boilerman there, or fireman there. And a lot of people lost their lives. Some people could not get out of the cars. It was a tragic accident, and the problem was fatigue failure in the axles of the train. If you think about a train wheel, the way it's set up, there's two wheels on either side and a solid axle between the two, and those axles are prone to fatigue failure. And initially, when people were designing these engines early on, all they knew about really was static loading, not this fatigue type loading. There was some people, I suppose, looking into fatigue, but it wasn't a real big thing until 100 people or so lost their lives in this rail accident, and then people became serious about looking into fatigue and understanding it and using their knowledge to prevent this sort of tragedy. I got information about this from this reference. I thought I would put it up here. It's a good paper. If you ever get the chance to read it, I would recommend it. It's very interesting, sort of a historical overview of what really gave birth to this the serious study of fatigue. Now, there's another section of fatigue we won't study. There's so-called low cycle fatigue. And if you look at the SN diagram over there, people disagree about where there's a cutoff between the two, but definitely 1,000 and below could be considered a low number of cycles. And what happens is that in this low cycle area, the amount of stress and the amount of strain applied to the material is pretty close to the yield stress or strain. And the only way to analyze this is with something called fracture mechanics, where you really need to know the geometry of the crack, and then the life of the part is predicted by the strain life method. We're not going to cover any of that because so much of what we're really interested in is high cycle fatigue instead. So this is the region for low cycle fatigue that we're not going to cover, anywhere from about 1 cycle to 1,000. Theoretically, the y-axis would be 1 cycle or very low cycles, and would be the yield strength of the material if you're assuming that yield is failure, which is the most common. Now, in this region, in this low cycle fatigue region, you can characterize the relationship between the stress amplitude and the fatigue limit or the endurance limit of the material. And this equation here just relates the two to one another. And there are some values in your text for various materials for the constants N and B, but again, we're not really interested in that for this course. For high cycle, anything above 1,000, some people would say 10,000, some people would say 100,000 cycles, but more than 1,000 for sure is high cycle fatigue. It's out there somewhere. So we're looking, in this case, your author says 1,000 and up. That's the area we're particularly interested in. And so what we're really wanting to get here is the endurance or the fatigue limit. Now, that's not the highly sloped section up to, in this graph, 1,000,000 cycles. It's what comes after that. It's the endurance limit where we don't have to worry how many cycles we put on the part anymore. It simply will not fail. And of course, for steel you can say that, but for aluminum you can't, because aluminum still will tend to accept lower and lower stresses at higher and higher numbers of cycles without failure. So you have to derate the stress at higher cycles for aluminum. So the so-called endurance or fatigue limit for aluminum is usually published at about 1 million or 10 million cycles, but you got to understand that you can't have as much stress if you have more cycles than that on the aluminum part. I'll reiterate that steel can have an actual infinite life as long as you keep the endurance or fatigue limit or the fatigue stress low enough, but aluminum cannot. So when we're testing this, we use a rotating endurance test, and what's kind of interesting about it, if you think about it, is that with the shaft rotating, the stress is actually, and I've got, I've made a mistake here. I've got the shear stress. I should have had the bending stress here. I put the wrong symbol on it. It shouldn't be tau max. It should be sigma max. So the bending stress is maximum at the outer fibers, the top and the bottom of the cross section. So if you think about the way the stress is distributed, really the stress is maximum at the outer fibers, and that's where failure is going to occur the soonest, right? But not all of the bulk of the material is stressed equally, right? It's just mainly the outer section. Now that's not the only way to do it. That's where the bulk of the data comes from, is that R.R. Moore type of fatigue test. So if you look up this type of SN curve, that's probably where the SN curve came from. However, today people are doing more with programmable direct axial loading type of servo driven machines, where you can take a sample and you can apply a load to it over and over. And so if you think of just a simple thing like this ruler here, if I wanted to fatigue test it with one of these, instead of rotating and bending it as it rotates, what I'd be doing with this servo is pulling on it over and over to some programmable position. So some programmable load of compressive stress, tensile stress, whatever I wanted. I could program it to apply whatever loads I want repeatedly in order to test the material and find its fatigue life. Now, interestingly, if you're doing it that way, instead of bending, you're not just loading the outer fibers, you're loading the entire cross section at the same amount of stress. Now, this type of test usually predicts about 20% less life for the same kind of material that the rotating or the R.R. Moore test would predict. So it can be very useful. We've even got some former students who are working for companies where they're doing exactly this. They've got high life, high cycle cylinders, hydraulic cylinders, applying loads to structures repeatedly, however they want to program it, to see what it takes for that structure to fail. Now there can be an effect of the mean stress. If you think about the rotating bar or shaft that we were talking about before in the R.R. Moore test, the mean stress is 0. But if we can program it and we can apply tensile stress continuously, just more and then less tensile, more and then less tensile, but always tensile, then the mean stress is not 0, and that can have an effect on the resulting life. Now when these tests are performed, they're performed under ideal conditions. So the stress and life relationship that you get from them is very idealized. It doesn't represent real world behavior of the material. And so things that can go wrong are things like, well, surface finish. If there's not a perfect surface finish like this polished sample we're talking about, well then the part simply will not be able to take as much stress because it's easier for a crack to propagate from the surface in that case. Now, we always begin by assuming that the endurance strength is about 50% of the ultimate strength of the material. The correlation works fairly well when you have a very polished surface. So you notice the polished line there. If we look on the x-axis for tensile strength, let's go all the way to the right at 220 KSI. You'll notice if you count off the minor divisions that the y value of that right point of the polished line is at 110 KSI. And then the left point, you can calculate that as well. 50 KSI all the way on the left-hand side matches with 25 KSI or 25,000 PSI on the y-axis. So that's the polished line. That's the ideal sample. But if instead of having such nice surfaces, if there's a different surface finish, like if the surface is ground instead of polished, if you don't go quite all the way to polishing, then you have to derate the strength of the material. So this this actual endurance strength of the material is not a material property. Well, it's sort of a material property, but it's affected by other things. It's affected by the surface finish. Some metals are strong, but they're simply forged, so they're beaten into their final shape. And when they're beaten into their final shape, the surface is not all that high quality of a surface. It can be a very rough surface, and so that does increase the likelihood of fatigue failure. Now, we don't just have this chart in English units, we have it in SI units as well in the text that I've referenced, so make sure you know where that's at. But anyway, these two are nice charts because you can, if you know the ultimate strength of the material and you know how it's finally processed in its final form, you can go up to the curve and read off a theoretical endurance limit that takes into account the surface finish on the material. So this is a handy chart, and we will use it quite a bit. Now, another important thing to realize is that after the part is made and when it's put into service, if the surface is damaged, well, then there goes your endurance strength, right? Because now you've got a place where a crack can propagate, and so it's a weaker part than it would have been otherwise. So surface damage while in use is a real problem. One thing to note about this, this data was taken from a reference where the author said that you should not extrapolate the right-hand side of this. So at 220 KSI, cut it off. At 1500 megapascals on the right-hand side, cut it off. You don't want to go beyond that because he said the data beyond it was inconsistent. So don't extrapolate this chart, please. Now, what about actual conditions? What about real-world behavior of material? How could we get to that level where we can predict what real materials and real parts are going to do? We'll call this Sn prime the actual endurance limit, although it's not really the actual, it's just a better estimate, I would say. The way we'll calculate is we'll take the endurance limit that includes the surface finish of the part and add some correction factors to it, these C factors. You want to note the procedure on page 178. It's a page you should become quite familiar with. We'll use it again over and over. The first modifying factor is a material factor. Now, this will sound a lot like what we've already said, but this is a factor that depends on how the part is made. So if the part is, you could have the same alloy, the same chemistry of metal, and yet have different processes for making it. You could use powdered metal to make the part. You could use wrought methods to make the part. You could do all sorts of things. And so the way that that material is put together and formed will affect the strength of the material throughout the body of the material. So whereas we've already taken into account the surface finish due to the processing, now we're taking into account how the entire bulk of the material is processed, and there may be cracks within it, or maybe the material doesn't form together quite so well, or different kinds of grains perhaps are formed, whatever the case may be. This material factor takes that into account. Now, I'm not going into the details of these. You can find all the numbers you need on page 178 and in that area. Just look at the procedure and you'll find it. The next factor is a type of stress factor. Remember, most of our fatigue data for SN is from rotating tests, right? The RR Moore tests. If the test, or if the condition of loading to the actual part is not that kind of stress, it's not a bending stress where only a small section of the material is stressed, like for example again with this ruler, if I bend it, mainly the stress is in the top and in the bottom, right? That's where the largest stresses are located. But if that's not the case, if I've got a stress where the entire cross section is being stressed to the same amount, then that has to be taken into account. The measured amount of SN has to be modified, and that's what the type of stress factor is for. It's one of two. It's either 1 or 0.8. And so it's 1 if the type of stress is just like a rotating shaft, it's or a bending stress, and it's 0.8 if it's an axial type of stress instead, where the entire cross section experiences the same stress. The reliability factor is next, and if you think about the way that the SN curves are usually made, well, experiments are performed and then that data is just best fit. Well, that means that the line is at the 50% failure, right? So 50% of the, consider one particular SN pair, right, from that line. If you ran 10 experiments there, you would expect half of them to fail at that number of cycles and half of them to not. And 50% reliability is probably not good enough for most machine designs. I mean, how would you like it if your car failed 50% of the time when you tried to use it? You probably wouldn't like that. And of course, you know, even to get a 50% reliability in your car, each component actually has to have a much higher reliability than 50%. Because if any critical component fails, then the car doesn't run. So here are some factors that you can put in to have reliabilities other than 50%. You'll almost always use one of these, depending on what reliability is desired. The size factor is another factor that's really important. We're going to talk about this one quite a bit. The idea here is that, you know, we start off with a rotating sample that's 0.3 inches in diameter, right? So 300 thousandths in diameter. If you think about the stress gradient, or in other words, how quickly the stress changes as you move toward the outside of that bar, you realize that as you go to larger and larger sizes, the stress gradient changes. And because of that, we have to take the size into account. The net effect is that the endurance strength is reduced at larger diameters. That's the net effect here. And you can see that on the chart here, depending on the nominal size of the shaft or whatever the component may be. Of course, we're talking about shafts in this case because we're talking about a diameter. But as you go to larger and larger diameters, the size factor goes less and less below 1. In other words, you're taking more and more away from the experimental result, the SN experimental result, to get an actual result or an actual predictive, you know, ability. Now, you don't have to use that figure. There is a table with equations in it. You can use it. It's got SI and customary units. So if you want to use it in a spreadsheet, you can. This is just a curve fit of that equation. That's all it really is. Now, remember, what we've been talking about so far is all for normal stresses. Even a bending stress is a normal stress, so it applies here. We're not talking about shear stresses. Like I said, if you want to understand shear stresses, read in the book about how you combine. You just use Mohr circle and then use either distortion energy theorem or another one. I can't remember the other one right now, but one of those two is what you use to basically combine the stresses after Mohr circle into something that sort of generalizes the approach that we use here. Now, there can be other factors that should be used for getting at the actual endurance strength of a material. There are other size factors, other conditions to be considered. What if we have a shaft that's not rotating? What if it's a round shaft and it's not rotating? What if it's not round? Then what do we do? Well, there are ways to approach this, but we have to define what's called the A95 cross-section, or circular, rotating circular cross-section. And that's best understood by looking at this figure. Before we approach the non-rotating and the non-circular cross-sections, let's just think for a minute about the regular R.R. Mohr test with the shaft rotating, and you know, every point on the outside experiences stress and it's fully reversed and so forth. Okay, if you think about the stress in that cross-section, which is what we're looking at here, it's all a bending stress, right? And so that bending stress increases as you move farther and farther from the center to the outer fibers, right? The upper and lower outer fibers. But since the whole shaft rotates, it's, you know, the whole outside that experiences that maximum stress. So the stress, the magnitude of the bending stress, is just proportional to the radial distance from the center. And then you know that because you could calculate the bending stress as mr over I, right? Where r eventually becomes c, the outer radius, and that's the maximum stress. Since the stress is proportional to the radius, what we're going to do is try to define an area where the stress is at least within 95% of maximum. Because if you think about what causes fatigue failure, it's high tensile stresses, right? Well, where do high tensile stresses occur? Obviously at the surface, but also, you know, 95% of the maximum stress is still quite a bit of stress. So we're going to try to look for the area where the stress is at least 95% and above of the maximum stress. And since the stress is simply proportional to the radius, this is a pretty simple thing. All we need to do is calculate the annular region that's in pink there, And here's the equation for it. It comes out to 0.0766 times the diameter squared. Okay. Now this is just for circular cross-section. We have not approached non-rotating or non-circular cross-sections yet. If we think about a hollow cross-section, since the hollow section doesn't take much stress, in fact, I mean the stress is relatively low there, right? The 95% and up stress, and 95% of maximum and up stress is near the outer surface. It's not necessarily at the outer surface, but it's near the outer surface, and as long as that inner diameter, lowercase d, doesn't get too large, the place where fatigue cracks are going to start growing is probably in that outer area. So what we're doing here actually applies to circular cross sections as well that are hollow. So all those factors we saw before, all those size factors from the chart and the equations I showed you, they apply equally well to hollow cross sections. Now I'm not talking about a hollow cross section where you have a very thin wall or something. Obviously that's a little different. But those size factors can apply as long as the hollow section is, reasonable size. So finally, what about a non-rotating circular cross section? So we'll keep the cross section the same, but what if it's not rotating? Then what? Well, what we're going to do is we're going to consider the A95 area of that cross section, and we're going to try to find an equivalent diameter. So if we have that exact amount of area, but we spread it out over an annular region, what diameter would we end up with? That would be the effective diameter. Now you need to pause and think about this maybe a little bit, but it's pretty straightforward if you think about it, because really we still have bending stress, right? I mean, we're still taking this round section and doing this to it, right? So there's going to be maximum stress at the upper and lower, the outer fibers. We're assuming that it's bending about a horizontal axis, obviously. And the 95% stress area, the area that is stressed to 95% of the maximum stress, is pretty easy to calculate, because still the stress is proportional to the distance from the center. And so at a distance of, a radius of 47.5% of the diameter, that's where the 95% of the maximum stress is going to occur. And then as you move more and more towards that upper point, the outer fiber, or the lower point, the outer fiber, the stress just goes finally to the maximum stress. So that's the area, or the region of this area, that is stressed to 95% of the maximum stress. Now, from the geometry of a circle, I'm not going to show you the details, but from the geometry of the circle, you can find that the A95 area is 0.0105 times the diameter of that circle squared. Now if we say what round section, what annular region in a round section, what size would give me an equivalent amount of area. In other words, if we set this area in this non-rotating to the area in a rotating shaft, we can calculate a so-called equivalent diameter. And you can see it's been done here, 0.0105 d squared. That's the upper and lower regions, okay, from item C, is being set equal to a shape like item A, 0.0766 times a diameter, an equivalent diameter squared. And then the equivalent diameter is simply being solved for in terms of the diameter of the original shaft. So if we know the diameter of the original shaft that's not rotating, then 30% of that diameter is equivalent to a shaft that is rotating. And then we can use size factors that are based on that equivalent diameter. So what you do is you take this equivalent diameter, go to that chart I showed you, and look up the size factor from the equivalent diameter, not from the actual diameter, if the shaft is not rotating. Now we can also do this for a non-rotating and rectangular cross-section, for example. You can do it for any shape that you want. It's just these two shapes, a round and a rectangular, are fairly easy. And so if you think about how this works, the area that is stressed, well, it's still, it's still the outer regions where you're going to find stresses up to 95% of, well, 95% and beyond of the maximum stress. If you stop and think about it for a second, I think this figure will make some sense. I'm not going to go into the details of how they came up with this. It's actually pretty simple. But the A95 area then is the upper and lower area you see in pink in item D there, and that's just 0.05 times the height times the base. Okay, so if you add those two areas together, it's The upper area is 0.025H, the lower area is 0.025H, add them together, that's 0.05H, multiply by the width B, and now you've got the area. Okay. Now, again, we're going to play the same game. We're going to set this equal to an equivalent annular region of a circular cross-section that is rotating. So 0.0766 diameter equivalent squared again. Solve for the equivalent diameter, and here you have the result. If you know the height and base width of the rectangular section, just plug it into this equation and you can calculate an equivalent diameter. Use that equivalent diameter then to get a size factor for this non-rotating rectangular cross-section. There are yet other size factor conditions. What if the type of loading on the part is direct axial tension? Well, the idea behind the size factor was that there would be a gradient, right? That there would be a stress gradient, a change in stress versus change in position. And that gradient is what would give rise to a size factor that would derate the endurance strength of the material. But if we have direct axial tension, then the entire cross-section is stressed the same, which is going to cause fatigue at any point, right? At any point is equally likely to fatigue, and so then the size factor should be 1. Now you might look at this and say, well, wait a second. I thought you said that the size factor was 0.8 if it was direct axial tension. Don't confuse the various factors. The type of stress factor was 1.0 if it was bending stress. It was 0.8 if it was axial tension. But the type of stress factor and the size factor are two different things. Right? The size factor has to do with the idea that if you have more material and it changes the gradient, the stress gradient, then you might need this size factor. So since there is no stress gradient, we just use a size factor of 1 in that case. Now that's actually the last factor that we'll quantify in the course. There are other factors, though, you should be aware of. For example, flaws. If the material has a flaw inside of it, that can cause problems. If the material is cast, for example, castings are very likely to have missing material, inclusions, whatever the case may be, that will weaken the material. And if you can't x-ray it and measure them and know what those flaws are and compensate for them, then you should probably increase your safety factor and derate your your endurance strength quite a bit, or maybe even test some samples and try to get a good handle on what your average and high and low, your range and variation of endurance strengths would be given that casting process and material and so forth. So flaws can cause a lot of problems in material and reduce the endurance strength. Temperature can cause metals to be weaker as well. A temperature of about 500 degrees Fahrenheit and up will certainly weaken metal. So anytime a part is operated at a high temperature, you need to take that into account because it will reduce the endurance strength of the material. There can be non-uniform material properties in materials. If you think about welding, for example, you can see how this looks like a great weld bead, but has probably affected the material properties around the weld bead. If you have, the annealing can change material properties. All these different things affect properties. In fact, welds can cause tensile stresses in materials, and tensile stresses are the benefit of fatigue. Right? Fatigue benefits from tensile stresses. Processing materials can leave behind tensile stresses. I was just watching a video the other day because I bought some I-beams about how to straighten structural steel. And there's a process called flame straightening where you purposely heat up material. That material deforms and you end up with all kinds of fairly complicated stress distributions within the material, tension and compression, that affect the material's properties. Now, of course, some materials are processed in a certain direction. Think of rolling out hot rolled steel or cold rolling material. And what that ends up doing is making the properties different in different directions. So you might take a part that's been drawn or rolled in one direction, made a shaft out of it, rotate it, test it, and you're testing the strength in the direction of the processing, right? So it might have higher strength. And then if you load it in the other direction, in the cross direction, across the processing direction, you could get different properties. So it's very important to realize that all these different factors can affect the material so that it has non-uniform properties and doesn't necessarily behave in the way you would predict from a simple test that only considers one direction of the material's properties. So here's an example where some materials being cold rolled, and so obviously the materials are going to vary depending on, the properties are going to vary of the material depending on what direction you measure them in. Also, this type of process can, in most processes, can leave behind residual stresses. If you're too aggressive at material removal, for example, yanking out material, that can pull on other material, leaving behind permanent tensile stresses. There can be compressive stresses. Here we've got two rollers compressing material together. Now, compressive stresses are usually good, whereas tensile stresses are usually bad. So tensile stresses, as I said, are they help fatigue occur, and so we'd like to avoid them. But anytime you can make compressive stresses, like shot peening, for example, where you just squirt out a lot of shot at high velocity of the part, basically what you're doing is you're compressing the surface of the material, leaving behind residual compressive stresses. And this can be good because as the part is loaded, the surface has to be, it has to have a decent load to overcome the compressive stresses in the first place and get into the tensile region. So that can actually be a very good thing. There are other methods also of generating compressive stresses in a surface. So besides shot blasting, there's also peening, where basically you're hammering the surface in order to create compressive stresses in the surface. And so here you see an ultrasonic peening machine that is hammering the surface at a very high frequency in order to leave behind compressive stresses and help this weld not cause failure from the tensile stress that was left behind there. Corrosion and the environment that the part is in can make a difference. Most people think of rust when they think of corrosion of steel. That's certainly one way. Materials such as aluminums, of course, can be corroded in other ways. And of course, the problem here is that the surface becomes imperfect. It becomes more rough, and so it's easier for a crack to propagate from the rough surface. But there's also hydrogen embrittlement. If you have a steel, especially high-strength steels, and in a hydrogen environment for whatever reason, that hydrogen will basically attack the steel. It'll diffuse through it and cause essentially crystallization of the material, where it breaks apart essentially and becomes brittle and not a very good material for taking tensile loads. So depending on the environment, there can be other things as well, of course, but that can cause trouble that would derate the endurance strength of the material. Nitriding, on the other hand, is a process that increases the strength of the parts or whatever is made from the steel typically, and it's usually operated at a high temperature and in an ammonia-rich environment so that you can get the nitrogen. It's a surface treatment that can significantly affect the endurance strength, and in fact it's the only one on this list that can increase the surface strength, besides leaving behind compressive residual stresses in the material by either shot peening or shot blasting or by peening the surface. So this is another surface procedure that can increase the endurance strength of parts. The stress ratio can also have an effect. Now this chart you're not supposed to use for any actual design work. It's more of a schematic. It's more of a prototype, if you will, to show you trends of things, not actual data. And so what this is showing you is the effect of the stress ratio. Remember, the stress ratio is the minimum stress of the cycle divided by the maximum stress of the cycle. And so at a stress ratio of 1, well, that's a static load, right? Because at a stress ratio of 1, the maximum and minimum stresses are equal to each other. That's how you get 1 out of it, and that's just a static load. And so that's the upper line of this figure. There's no effect on the stress, the ultimate stress the material can take. And notice we've got ultimate stress on the vertical axis. But as you get into fluctuating tensile stresses down to R equal 0.6 and 0.25, then you see that the effective maximum applied stress as a percentage of the ultimate strength goes lower and lower. And so that's problematic, right? Because what are we doing? Well, let's see. At an R of 0.6, well, that's a minimum stress that's still positive. These are both positive stresses, the max and min. But you know, we're not too far off. As we go down to R's that are lower and lower, what's happening is the minimum stress is going lower and lower by comparison to the maximum stress. And we're getting lower numbers till we finally get to the point where we have just R equals 0, and in that case what we've got is a pulsating stress, right, where the minimum stress is 0, the maximum stress is some tensile stress, so we get just 0 from that. If we get to the point where it's partially reversed, where the cycle now is moving down farther again, so we still have a positive tensile stress, but a negative, a compressive stress for our minimum stress. Well, then the negative stress in this case is half of the maximum stress, and so it's partially reversed. It's not fully reversed, it's just partially reversed. But the worst case scenario, where we have to derate the strength of the material the most, is where we get to that fully reversed stress. And you might say, well, okay, all this makes sense, but I remember that those fluctuating stresses went down farther, right? We eventually got to a point where we went past the fluctuating stress, where the maximum stress was a positive number and the minimum stress was the absolute value, was the same value as the maximum stress. We went further down than that. Well, it turns out that, again, tensile stresses are really what encourage fatigue, not so much compressive stresses. And so really for compressive stresses, that's not near as much of a concern or something we're interested in with this type of diagram. Basically the curves would start to go back up, or they would just be at the static position depending on how the loads are applied and so forth. So we're really interested in tensile stresses. So the stress ratios we consider are those that include tensile stresses. And so since we're using the R.R. Moore test, that's a fully reversed test, and that should give us the worst case scenario, right? The minimum endurance strength. So therefore that's the most conservative type of test. Okay, so there's this thing called fatigue. How do we design to protect against it? What should we do? Well, it depends, because remember there's two parts to the fatigue load. There's the main stress and the alternating stress, the stress amplitude. But we're going to do the same thing we've done before. We're going to compare the stress in the material to the material strength. What can the material take? Now the strengths we've got so far are the ultimate strength, the yield strength, and now the actual endurance strength, which is a hopefully correct endurance strength. Now what we're going to do is make a diagram that has the mean stress on the horizontal axis and the amplitude, the stress amplitude, on the vertical axis. Okay, and then if we think about what this means, well, at a amplitude of 0, the mean stress is just going to be no fluctuation. It's just going to be some stress, right? Some value of stress, some static stress. In that case, we could look at and consider either the yield strength or the ultimate strength of the material. Probably yield, because we don't really want our parts to deform plastically, so we'd like to keep the material stress below the yield limit. So on the horizontal axis, the yield stress would be a natural point to consider as a limit. Everything to the left of that would be okay. Now on the vertical axis, you might initially think, well, why not just use the yield strength on the amplitude axis as well? In that case, if we then connect those two lines, our theory could be that everything would be safe below that line. So the equation of that line you can see over there on the left-hand side, and it's written so that you can tell that the stress amplitude is being compared to the yield strength, and the mean stress is being compared to the yield strength as well. So there's the equation of that line. Now, obviously this is not going to work, right? Because if we have a stress amplitude, if there's some mean stress, or if there's not, whether even if it's 0, so at the vertical axis, if the mean stress is 0, that's just a fully reversed bending stress, right? There's still a stress amplitude there potentially. if we compare that stress amplitude to the yield strength, this is not going to work. That was the whole point of fatigue. So this idea is not a very good one. Okay. On the x-axis, it's okay, because the x-axis, that point that I've got a check mark on, has zero amplitude, so a constant stress, as long as that stress is less than 1, or that stress ratio between the mean stress and the yield strength is less than or equal to 1, the material should be okay. It's the vertical axis we have a problem on, that point where we just arbitrarily plot down the yield strength on the axis and said, well, if there's no mean stress, but the amplitude of the fully reversed bending stress is less than the yield strength, then we're okay. No, we're not. That's what fatigue is all about. So this won't work very well. A natural change to that would be, well, let's use the actual endurance strength on the y-axis, because that should take care of it. And then really the value of what we did a minute ago was this idea of connecting the 2 points with a line. And the idea is that if the mean stress is not at the yield strength, if it's less than that, say it's half or so, okay, then we should be able to tolerate some amplitude of variation. What would that amplitude be? Well, we're basically assuming a straight line between those 2 points. So all we would do is go halfway between 0 and the yield strength on the x-axis, go straight up to the triangle, and then come over, or the hypotenuse of the triangle, then come over to the y-axis, and we'd find that the allowable amplitude of cyclic loading, if the mean stress is half the yield strength, would be half of the actual endurance strength. So it would be halfway between 0 and Sn prime on the y-axis, see? So that's a good idea. It's not too far from reality. This is called the Soderberg or Soderberg criterion. I'm not sure how you pronounce the name. It's a conservative estimate. It turns out that if you actually do the experiments, this works fairly well. It's not far away from reality, but it is conservative. Okay. Now, an interesting thing about this, and you can see the equation for it there on the right. I've got it circled with an ellipse in red. The interesting thing about it is that notice we've applied a stress concentration factor to the amplitude stress variation, but not to the average or mean stress applied to the material. The reason is because research has shown that stress concentration doesn't really affect how much the mean stress contributes to the fatigue, so to the fatigue failure. So there's no point in including it. We only put the stress concentration factor on the amplitude of the varying stress. Now notice we've set this equal to 1 over n. It's not just equal to 1 anymore. What's going on here? Well, the n represents a factor of safety that we might want to pull this line back from actual data to make sure that it's safe. So it's just including a factor of safety there. The Goodman criterion is a little bit closer to the actual data, and you can see data there in green dots essentially. The Goodman criterion is closer. What it does is it substitutes the yield strength on the x-axis for the ultimate strength. So it's the same equation as Soderberg, but you notice that we've got, let's see, actually, looks like there's a mistake here, because in this equation, it's exactly the same as the Soderberg equation. I didn't notice that when I was grabbing these from the chapter in the text. Where you see the second term, the mean stress divided by the yield strength, that should be the mean stress divided by the ultimate strength, not the yield strength. And so that's something I missed. But anyway, I'll fix it in the slides before you get them. Again, we've got a 1 over n to include a safety factor in this, and if the change were made, then you see the area that would be considered safe. We've just substituted SY for SU in the horizontal axis, and that's the Goodman criterion. Now, the only problem with this, if you think about it, is that on the x-axis, where there's no amplitude of stress, there's no variation, it's just a constant stress, we're saying that it's safe to have an average stress up to the ultimate strength of the material. Well, that means it's going to yield. Now, notice that we've said this with a factor of safety 1 over n. So we really need to check to see if yielding actually occurs by saying, okay, let's forget the factor of safety for a minute, and let's just consider what would happen if if we didn't have that factor of safety. And so this check here that you have to perform includes stress concentration on the mean and the yield strength in the denominator. Here it is correct, and notice it's just equal to 1 on the right hand side, not equal to 1 over n. So this is a check that you have to perform to make sure that the material will not yield at low cycling, low amplitude cycling. So that's a check that you have to add in if you use the Goodman line. The Gerber criterion is even more accurate. It's actually a parabola, and you can see it there. It's really just going through the data, and is a pretty good estimate of the actual relationship between how much mean or average stress is allowed versus how much amplitude of stress is acceptable. And again, notice that we've got our factor of safety in on the left-hand side now. That's because notice the second term is squared. It's compared to the ultimate strength, just like the Goodman line, but it matches the data better, and that's the Gerber criterion. So it's more accurate than the Goodman, but it's obviously less conservative because it has a larger region that's considered safe. I didn't draw this section. You can kind of see it there, everything under that parabolic line. There are other failure theory lines as well. ASME has one, and in that what they do is they basically use the Gerber parabola, but they replace SU with SY, and they actually square the first term as well. So it just depends on what area you're working in as to which one of these failure theories or safe zones you will use. Notice we've gone from most safe, essentially, except for the first one, to less and less conservative estimates of the relationship between the mean stress and amplitude stress that is acceptable.